Good morning, good afternoon, everybody. My name is Matthew Hurwitz. I'm on the AMD PR team. Thank you for joining us this afternoon, morning, for a deeper dive into Zen 5 architecture. As a reminder, all of the information included in this deck is embargoed until Wednesday, July 24th at 9 a.m. Eastern. You will also get a copy of these slides after the presentation. At the conclusion of the slide deck, we will be opening it up for Q&A. Please use the chat box in your Teams application to submit any questions you have as we go along. Today, we have Mahesh Subramoni, AMD Senior Design Engineer Fellow, and Mike Clark, AMD Corporate Design Fellow. With that, I'm going to go ahead and turn it over to Mike.
All right, thanks, Matt. So I'll jump right in. This is our next generation Zen 5 core cautionary statement. Guess I should go slow. Hopefully, these are updating fairly quickly. All right. So with Zen 5, our design objectives were, as traditional, deliver another major 1, 2, and 2T performance increase. But we really wanted to create a new foundation of compute for the future. And I think you'll see that as we go into the deep dive. And kind of also, we wanted to bring that AVX 512 onto a 512-bit data path so we could really get the full benefit of the ISA extension into vector throughput and AI uplift. At the platform support, we wanted to deliver both our traditional Zen 5 and compact cores. Because of, the different markets we go into, we want to make sure, even though all markets don't need that wide vector support, so have the ability to cut down the floating point to 256 very easily, while still maintaining good bandwidth in the machine and good energy efficiency. Support 2 technologies, 4 and 3 nanometer, and some enhanced ISA capabilities. All right, so here's just a first overview of the microarchitecture, and then I'm going to deep dive into each parts of the microarchitecture. But as always, we got our next gen branch predictor coming out. On the cache side, we have our traditional 32K 8-way iCache, although we dual ported it now, so it can do 2 32-byte fetches per cycle and feed that forward. When we've seen the instructions before, we put them in an op cache. In this generation, we're storing 6K instructions, and we can access that also dual ported, so we can pull out up to 12 instructions per cycle, and then we break them into ops if needed downstream. Our data cache, we grew to 48K 12-way. Our L2 cache was 1 meg, but we grew its associativity to 16-way. As I mentioned, we have the dual fetch and decode pipes, which we'll get to in detail. 8 ops per cycle. The execution, we grew to 6 integer ALUs, 4 address generations, so we can do 4 load stores per cycle, 6 floating point ops per cycle, reduced the FAD to 2 cycles, grew that data path capability to 512 bits, and 2 of which can be AVX 512 loads, and doubled the bandwidth from the L2 to the L1, and as always, supporting 2 threads per core. So as you can see, really a big new fundamental foundation for compute. Tradition looking at originally like from our Zen to Zen 4, we were pretty much a 4 ALU 6 op dispatch machine, which we did a lot of work to really mine that kind of limitation, but we really needed to grow that out. And as we grew that out, we needed to essentially grow, everything to really rebalance Zen for the new foundation going forward, so that, the future processors can then really optimize with those compute resources. So going back to the beginning of the machine, it all starts with our branch predictor. We have no bubbles when predicting conditional branches. We actually grew our L1 BTB to 16K, about the size of our traditional L1s before, and grew our TAGE capability. The return address stack for call return subroutine programming, we grew it to hold 52 entries. We can do 2 take-in branch predictions per cycle and have up to 3 prediction windows per cycle. We on the memory side, we have an aggressive fetch that's trying to hide any of the, our L1 is still can be small for, bigger footprint workloads. So we're aggressively fetching ahead to pull those instructions in from the L2 and even sometimes from the L3, or get those table walks going if there's a TLB miss. But we also grew on the I side, the L2 ITLB to 2K entries, again, for those larger footprint workloads. We can do 64-byte cycle fetch from the L2. And as we said, it's dual ported, so we can now, predict those, have a basic block up to a branch, go fetch its target, be fetching them both at the same time, as well as then obviously predicting that again and again. So really being able to, even if basic blocks are small, be able to feed enough instructions forward to feed that wider dispatch. On the decode, opcache, we grew it, its associativity 33% to 16-way. It's denser than our previous generation where we were storing ops. We're now storing instructions. And then if they are multiple ops, then we will break them out outside. This, we are very dense in our micro-op format though, so a lot of instructions do map one-to-one, as well as we have a lot of fusing we can do where we can actually map two instructions into one fused instruction inside the op cache. So it can get really dense to try to, again, maximize efficiency and that dispatch interface. Coming back over to decode, we have the two pipes of decode. So as we're feeding the two streams out of the iCache, we're decoding them in parallel. Each pipe can do 4 instructions per cycle. And then when we switch into SMT mode, we actually give each pipe to each thread. So then they can have a whole pipe dedicated to them, less less interference with the other thread as we're trying to, again, stream into this 8-wide interface. And as we'll see, we then feed 8-wide dispatch out into our coprocessor model of integer netp, as always been in the Zen line. So we do 8-wide dispatch, rename, and we retire 8 instructions as well. On the integer scheduler, we went to a more unified. In this generation, it has an age matrix to try to find the oldest instructions to schedule. With it unified, traditionally we had more, each ALU had a scheduler in front of it, but that had to be allocated at dispatch time. And so you can have inefficiencies on how you allocated based on dispatch versus how dependencies come back and things need to execute. And so this simplifies the pick, having it more unified, and you get more symmetry across our units. We also made our units more symmetric to help simplify that scheduler. When we went to 6 ALUs, we have 3 multipliers, and those ALUs are, the same, and we have 3 branch units. So you can see the scheduler can easily know which half of the ALUs it needs to go to if it has those particular instructions. We have 4 AGUs, or address generation units, to feed the wider load store unit, so it gets the right 4 memory addresses per cycle. And overall, we had to grow the window growth to support, all the new instructions we're now able to get in flight in the machine. The scheduler grew. We have 88 ALU entries and 56 AGU entries. It's kind of hard to compare to the past because, as we're more efficient with our unified versus distributed. So distributed always needs more entries overall, but we feel a really good balance point here for the way we've made these changes. The the register file grew to 240 entries. Be able to get all those, again, you get all those instructions in the machine, and the reorder buffer 448 instructions in flight. When we do go into SMT mode, we do statically chop that in half, but you still get an amazing 224 instructions in flight for each thread. All right. On the load store unit, as I mentioned, we grew our cache from 32K to 48K. It's now 12-way. But really, the design team's proud of it. Kept that 4-cycle load to use penalty. As you grow caches, it gets harder to it's a bigger. They'll keep the latency down, but they were able to hold the latency and not add a cycle for the larger cache. More bandwidth. We went from 3 pipes to 4, and made them fully capable as well, 4 loads and 2 stores per cycle. And we can do 2 loads and 2 stores, total combination of 4 in that number. We have, and we could also do 2 floating point loads per cycle, all the way up to even 512 bytes, 512 bits. Yeah, 2 store commits per cycle. And as I said, we grew that L2 bandwidth from 32 bytes to 64 bytes, both for fills and the victims going back out. On the TLBs, we again, as you can see, as we're getting more out of order and bigger, more instructions in, we need a larger TLB. So we grew the L1s. It was always fully associative with all page sizes. That's now 96 entry. And then on the L2, we went up to 4K, which holds everything but 1 gig pages. We smashed them into 2 meg in the DTO in the L2. For the loads and stores, we grew the queues. The store coalescing buffer grew. Our load ordering queue is more scalable than in the past. A little bit hard to compare with all the different dimensions. Data prefetching, we have a new 2D stride prefetcher that and doing so also improves the stream and region prefetchers. And we're better at picking up different patterns with our prefetchers. It's really important for us to, have good prefetching so we can keep ahead of those misses and be able to deliver the data as fast as possible as those new instructions are coming in. We want them to be able to hit that full 4-cycle load to use because we prefetch the data into the cache. All right, on the floating point side, we grew the data path to 512 bits. We have 4, baseline execution pipelines, 2 FMOLs, FMAs, 2 FAD pipelines, and then ability to do 2 stores, all independent. So if they don't have to share and do FP to ints over to the integer side for those type of instructions that are moving data between the floating point and integer side. As I mentioned, we can do 2 of those 512-bit loads per cycle, 1 512-bit store per cycle. We can still do 2 smaller stores, floating point stores per cycle. And we were a 3-cycle floating point add before. We were able to cut that down to 2 cycles in some scenarios. The execution within the floating point unit grew, what we call our non-scheduling queue grew. And with that 8-wide dispatch, we were able to get more floating point instructions into the machine, get more load stores in the machine so we can start prefetching their data. As the floating point instructions tend to have longer latencies than the integer side. So we want to get going on pulling their data in. So as they feed into the floating point machine, then the data again is also there ready for them. To grow those schedulers, we did bifurcate into 3 larger 3 separate schedulers, 1 pipe per pair. As you can see, we doubled the physical register file as we were growing with the data path going to AVX 512. We need a lot more registers to be able to kind of meet the floating point algorithms and hide the latency. And we kind of have to match the reorder buffer holds, of course, both integer and floating point. So we had to match that growth on the floating point side. All right, so that was a deep dive on the microarchitecture. We also, continue to provide both our classic Zen 5 and a compact core, and we do that in separate core complexes within the Strix SoC. Now the Zen 5 is our traditional optimized for maximum 1T performance. It has the high max frequency target. We pair it with more L3 per core. But then we have we can reduce that max frequency target to hit that max frequency target, we have to do a lot of custom logic. That ends up inefficiently. We have to break the design into smaller pieces, also inefficient, adds more area, things are further away, more buffering, more power. So lowering that frequency target, as you can see sort of on the graph, we can then pull the, break the design into bigger blocks, fewer bigger blocks, get the logic more optimized, get it closer together. It has the effect of reducing the power naturally that way. And then we can, you see it's the same, core design, same IPC, same ISA. We can then be more power efficient. Can't always hit that same max frequency, but we have, we have the classic cores there for that, and we can schedule them. And then we can also do power efficient work as we either scale out on a multi-threaded workload, or if that's really kind of only the use case for the machine, we can use the power efficient complex and power down the classic complex. We do actually lower the L3 per core on that one as well, just so we can, again, kind of get that scale out throughput. But we always have to be careful that, for true multi-threaded workloads that are trying to use all the threads, we can't compromise on the compact core because we're in that heterogeneous scenario. In our previous generation where these were in homogeneous SoCs when we were doing this, we had a little bit more flexibility to, because all the cores were the same in those SoCs, to modulate. But we have to be very careful here that we don't create a scheduling cliff with the two cores mixed together. But our goal is, yes, that we want to simplify the software scheduling. That same IPC means there's no unique bottlenecks. There's no different vector performance. The software can really just focus on whether it really wants to target that lowest latency, highest performing, or it really is working on a power efficient. They both support SMT, so there's no complexity there for the software to deal with. And even if they do make a scheduling mistake, since it has that same strong IPC, and it can quickly react and get the core in the right place, and it's not such a big delta overall. The new ISA for Zen 5, we have some new instructions, moved just some being able to do direct stores of different sizes, bypassing the caches. We support the VP2 intersect, which is a new AVX5 and 12 instruction that finds the pair intersection between a set of registers. We extended to VNI into the VEX encoding, the AVX512 back to the VEX encoding, so you can have more blended code. And we've gotten a lot of feedback from the community that they really wanted our prefetch was originally only into the data cache, and sort of with our split caches, if you wanted to prefetch in an instruction cache, you couldn't, the data side instructions were not appropriate. And so we created a dedicated instruction software prefetch. And for those large footprint workloads that even with us trying to, as far as we can get ahead, we're still not capable. If the program knows where it's going to be going, they can give us a hint through an instruction prefetch. And then we did add on the kernel virtualization side, we added some PMC virtualization, providing security between a guest and hypervisor. And for that heterogeneous SoC, we have a heterogeneous topology so that software can enumerate the different core complexes and understand how to schedule properly. Okay, I'm not gonna, on the left side is, I think all these are in the previous slide, so this is just put here so you don't have to look back through the slides. If you just want the raw numbers, they all should be here. On the right, as I said, we really fundamentally wanted to grow the compute capability within that mandated we needed to be able to provide enough instructions to do that compute and be able to balance out the latency behind it to really deliver, again, a new foundation, but balanced foundation to build on for the future. And as you can see, this is just, I mean, this is different, obviously, for different workloads. This is just kind of an example workload of where we attribute different goodness to. And then in the core complex, speeds and feeds, obviously we do a number of different complexes. This one is the Granite Ridge, but they do inherit a lot of these same properties. We doubled the L2 associativity from 8-way to 16-way. We doubled the bandwidth from L2 to the L1 from 32 bytes to 64 bytes. Kept our L3 as a low latency, but we now can actually have 320 in-flight misses in that L3. And all the goodness of before from Zen 4, where the L2s are fast and private. They're shared in the complex. It is L3 is a victim cache, so we get the full capacity of the L3s and the L2s. But we do duplicate the tags so that if there's a miss in core 0, it won't be in the L3 because that's a victim cache, but it's in core 7. We can quickly go down to core 7 within the complex and deliver the data back to core 0. All right. Mahesh?
Yeah, can you hear me?
Yep.
Yeah, so continuing straight down the path. I've always said when Mike delivers a core, I think we run with those cores into SoCs on the client space with both mobile and desktop parts. That's what we have done here right out of the gate. But as we said, the Zen 5 core complex, as we said, with that n number of cores with the last level victim L3 attached to it, goes in multiple flavors into multiple SoCs. The first is what we spoke about. The Granite Ridge SoC features 8 classic cores with a 32 MB L3. Up to 2 CCDs are featured in that SoC, so for a total of 16 cores, 32 threads, and 64 MB of L3. And that's a homogeneous architecture, really aimed at delivering that performance, that responsiveness across every core, across every thread, keeping scheduling and all things simple. Going down to the Strix Point architecture, I think you have 2 core complexes. You have a 4 classic 16 MB and another 8 compact, 8 MB L3 for the performance scale out you see from a perf power efficiency standpoint. Again, dual CCXs with asymmetrical L3 sizes, again, something that is we didn't touch upon quite a bit in when we spoke the last time, but that is a first for us to manage asymmetrical L3 sizes, whether it's server, desktop, or clients in the past. We've always had symmetrical L3 sizes. That does provide some amount of management that we have to do on our end. In terms of a view of a system is not symmetric. A view from a single core, if you look at, is not a multiplier. A factor is what this core sees multiplied by the number of cores is essentially what the system view is. Asymmetrical L3 comes with its fair share of challenges, and this is probably the first SoC where we have had 2 separate levels of L3s for core complexes and manage that quite effectively. And they're there for a reason. You have the larger L3 to support the performance scores for that responsiveness, and you have you're trading off area. Power is key, and so the amount of area we spent on each of these are scrutinized to the nth degree. Having that a smaller cache again gives you that efficiency when only that smaller core complex is lit up for those low utilization high residency tasks that we see commonly in notebooks. And as you look to the future, as Mark had indicated, there's going to be Epic that'll be anchored by the Zen cores, and there'll be smaller, larger CCXs that'll feature in everything from client to embedded and everything in the middle, right? So again, homogeneous or heterogeneous complexes are now available at our disposal to employ for each of these SoCs, and you will see quite a few of Zen 5 based products across our stack over the coming years. So taking a quick look into the Strix Point SoC, at the very top, like I said, anchored by Zen 5, the 2 core complexes, 1 MB L2 per core, 16 MB and 8 MB for the 2 core complexes. And the data path for each of those CCXs is 32 bytes per cycle for both read and write, going into the Infinity Fabric. Into the GPU, you have an 8 WGP or a 16 CU RDNA 3.5 engine. That's a typo. We should correct that. That's RDNA 3.5. And that is connected to the data fabric through 4 32 bytes per cycle port. Graphics workloads are more bandwidth sensitive and making their entire allowing it to take advantage of that large data path is something that's critical for us. Going to the third compute pillar, the NPU has a 4x8 array of an XDNA2 inference engine, and that is connected to the Infinity Fabric through a 32 bytes per cycle data port as well. In addition to this, we have a handful of accelerators and microcontrollers. I know we had touched upon this earlier on the APU front. There has been a shift, over the last 4 to 5 years from general purpose compute towards more domain specific accelerators. And again, the NPU is you could argue is one of those accelerators really catered towards doing power efficient math. And then on the other end, further improvements on all of our accelerators and microcontrollers. The video encode decode, the audio coprocessor, all for efficiency. The display controller, again, for simultaneous displays. And you have system management, a bunch of microcontrollers managing both power, security, manageability, separate controllers for certain IOs that we need to manage. So a handful of microcontrollers across the board to help orchestrate the system management functions within the system. And then as you look towards the IO, again, 128 bits of LP5 D5 combo, 7,500 megatransfers per second on LP and 5,600 on D5. 16 lanes of PCIe Gen 4. I know there was one session where the question came about that it is a reduction in lanes from 20 down to 16. Again, some of these were trade-offs in terms of pins and in terms of power, as well as us noticing that from a system standpoint, that additional 4 lanes were being used for a secondary storage, which didn't have a whole lot of attach. So we're taking away from that secondary storage a small additional flexibility that we had, which again we will revisit going forward. But for this instance, we cut those lanes down from the hawk point of 20 lanes of Gen 4 down to 16. Again, 4 simultaneous display streams and 8 USB ports, 2 USB 4 V1s. 1 USB 3 Type-C, 2 USB 3.2 Gen 2 Type-A ports, and 3 additional USB 2 ports for all the connectivity we believe is needed for that SoC, and of course other GPIOs, I2Cs, SPI, eSPI that round out what is needed for a mobile SoC. Clicking forward. Just a quick deep look into what the RDNA 3.5 improvements were. Again, the 3.5 should indicate that it's not a generational jump in architectural improvements. Want to make sure that is clear. It is, as Mark had mentioned, a squeeze of the power efficiency that we could get out of this engine based on the legacy of partnerships we had with our mobile friends. And so bringing some of that efficiency into the engine was the main driving force here, but we did put in a larger engine. So driving those efficiencies affords us to put a larger engine. So it is a 8 WGP engine, like I said, 1 SC, 2 SA, 4 WGP, 4 RB plus, 8 WGP, 16 CU engine. Again, maintaining that Fmax. Resulting in a 30% higher T-flops compared to the prior generation. So it is a larger engine. That is how we're getting most of the performance uplift here, to be honest. But again, the efficiencies we have done that from a power performance per watt and performance per bit standpoint allows us to squeeze this engine into that small TDP budget that we have. So just quickly touching some of the subsystems from a texture subsystem standpoint. Again, 2x sampler rate, subset of some of the most common texture sampling operations are now double rate. So the texture pipe can now process 2 quads of samples in parallel for 1D and 2D textures for some specific common formats. So this is a significant speed up for some common game texture operations. Point sampling acceleration. So that's hardware detects the use of flat point sampling and steers these sample ops down a faster, lower power processing path. So again, saving power. Another thing we didn't note here is decompressed texel reuse. So there's new hardware that allows multiple requesting ALU lanes to potentially share output from the same texture pipe decompressor. This allows the GPU to save power by turning off some of the unused decompressor. So small tricks in the texture subsystem to allow us to get that efficiency out of the system. From the shader subsystem standpoint, again, 2x interpolation and comparison rates. Most of that rich vectorizer for interpolation and comparison is now double rate. Both of these operations are pretty common in graphic shaders. There's floating point support in the scalar ALU, so this increases the efficiency of any wave uniform compute that needs floating point, starting to become more common in some graphics techniques. So we've added that in. And then Mark touched upon this new SALU instruction. It tells the shader processor that it can skip a single use VGPR, right? So lots of these instructions create a result that is immediately or used once and then discarded. So the RDNA 3.5 now allows hardware to detect that and forward that result straight to the subsequent instruction, skipping that, right? So all of these changes kind of improve performance and efficiency. Going quickly to the raster subsystem, so RDNA 3 processes geometry in batches, right, to minimize external memory accesses. RDNA 3.5 takes a step forward. It adds support for breaking those batches into smaller sub-batches. So this allows the hardware to be more efficient in general, especially when batch reprocessing is needed. This becomes really helpful. It also adds programmable bin order. So this increases the likelihood that the first bins of a new batch are the last bins of the prior batch, so essentially temporal locality. All of these drive towards reducing the amount of external memory accesses, right? Temporal and spatial locality, as Mark had mentioned. Again, performance per bit driving to the bottom line of being more power efficient. And at the very end, memory subsystem improvements. Again, LPDDR5 operates slightly differently than G, so being aware of that and getting more hits to open pages, improving efficiency there, as well as improved compression. During graphics rendering, it is typical to want to write a color render target and then attach it later to a read write for a different part of the frame. So RDNA 3.5 improves the ability to generate these larger block writes, right, more often, so they can be decompressed later. So just improves the memory compression overall and then driving that efficiency to the system. So if we click forward, I'm not going to go into details of this. There was a breakout session around XDNA2, but just hitting the key points here. Again, broad AI model support. Again, the pedigree that that Vamsi spoke about in being able to design these engines for multiple generations, bringing that experience in here. It is a configurable machine. It has that flexibility of being able to adapt to evolving models going forward that can take advantage of the concurrency. From a peak performance standpoint, it's 50 intake tops, can block float FP16 that we spoke about, the throughput of 8 bits, but with the accuracy of 16. Again, data types is really important, and driving that. And I think you're going to see that a lot of our competitors are going to start moving in that direction as well, trying to find more efficiency in data types where you get that efficiency while not impacting throughput, right? So I think we're breaking breaking ground there and saying driving people more towards accuracy than just concerned about peak tops. Tops is not created equally. I think we're going to learn more about this as this space evolves more. Gen on gen, I think it's just 2x more concurrent spatial streams, more memory capacity on die to feed those engines. Again, on a per tile basis, we have doubled the MAC as well, so we've grown the engine that way as well. At 50% weight sparsity and enhanced support for nonlinear functions, and all of these are just the design that we pull forward from our legacy of building these machines in the past. Again, improved power efficiency, right? Having a large engine like this and not being able to extract power efficiency out of it would be a crime. When we get to a point where you are able to confine effects and applications to run on columns or column pairs, being able to power gate those additional columns completely and have a data path that needs to be lit up only for that use case, I think is going to bear fruit. Right now, we're throwing everything at a common engine, treating this compute like a single compute with one large memory. Even though this design can evolve to look like that with our adaptive mesh interconnect and the way we have that last level memory and how we manage it, we can make it look like that large engine. I think we have taken on some burden of adding this flexibility, and we believe it'll bear fruit as the software evolves to having this run always in the background and having only a subset of this engine needed to satisfy those requirements. So next. And just rounding off the last SoC, the next SoC that we introduced is the Granite Ridge SoC. Again, the I/O die that we have here was unchanged from the prior generation, the Raphael SoC or the 7000 series desktop part. So that allows us to run to market as quickly as possible and again fit in that same AM5 platform infrastructure, which we believe is a key tenet for us and an important value add for our end user. From a CPU standpoint, again, up to 2 8-core 16-thread complexes, 1 MB L2 per core, 32 MB of L3 per CCD. As Mike mentioned, the 512-bit data path for the FP. But again, this core is optimized both from our process node standpoint as well as the design for high frequency. The data path is 32 bytes per cycle, each port. So each CCD will have that data path coming into the I/O die. The GPU remains the same. It's a 1W GPU, 2CU RDNA 2. It's a minimalist configuration really needed just to light up displays, if you will. And again, because of that reduced engine, it has a smaller data path, just two 32 bytes per cycle ports going into memory. It does have the video encode decode, the audio coprocessor and display controllers, and system management and security, just like it did with the prior generation. On the I/O front, again, 128 bits of DDR5, 28 lanes of PCIe Gen 5 here, and 5 USB ports, 3 Type-Cs, 1 Type-A, and then one, again, USB 2 port as well. Can support 4 simultaneous display streams and has all of the I/Os needed for, again, I2C, SPI, and GPIO. So again, from a I/O die standpoint, reusing exactly what we had in the prior generation, allowing us to fit into AM5. The CCDs did grow in size to afford the IPC and performance improvement that Mike spoke about, but then work on the packaging front to be able to fit that larger CCDs into that same AM5 infrastructure, so that the users can benefit from reusing their platforms for another generation was again a key design target for us going forward. So with that, just summarizing, I think as Mike said, AMD delivers again and Zen 5 delivers again. Another on cadence major performance increase. Balanced cross-core 1T 2T instruction and data throughput. The AVX 512 support with the 512-bit FP and efficient and performance configurable solutions with scale, right? With Zen 5 and Zen 5C and multiple processes across the entire product line. And that goes into the Strix Point and Granite Ridge SoCs. Strix delivers increased compute and efficiency across the entire chip with a no compromise AI PC solution, and on Granite Ridge again, commanding performance there, gaming leadership, and continuing our support of the AM5 infrastructure. So with that, I hope it is clear that AMD continues to drive leadership in both performance and efficiency. And I think any other closing thoughts, Mike, before we open up to questions? That's all I had.
Yeah, I would just say, also it's a new foundation going forward, so we'll be able to continue to stay on this incredible delivery of cadence of performance.
Awesome. Thanks, gentlemen. So we do have some questions. Just a reminder to everybody, we're only going to be answering questions in the scope of this briefing. We're not going to be discussing potential or future products. It's really just a deep dive focus on Zen 5 architecture that Mike and Mahesh just went over. So that being said, let's jump into some questions. I don't know who to direct this to, so whoever wants to answer it, just jump in. So our first question is, how does a selectable AVX 256 512 data path work? Is that configurable on the SKU level or just once during chip design?
Well, I mean, when you pick the 256, physically you can't go to 512, but no, we do. We actually on the 512, you can dynamically change into 256-bit mode if that were desired. And so we actually have built the kind of the load store side of the machine always runs in 512 mode, if you want to think of it that way. It's always delivering that data. And so also even from a data movement perspective, we can still maintain that high throughput. But yeah, you can. We can have a physical product that's 256. It can be set, you know, statically at boot, or it can actually even be runtime dynamically changed.
Awesome. The next one, what is a prediction windows? Is it the same thing, or is it the same as what is known as instruction block?
Maybe you can think of it that way. Maybe that's probably a AMD internal term, but as we're trying to maintain with all these things we're predicting, we're trying to also maintain all the instruction pointers and all the backends. So we have to continue to be efficient in other structures, and so having 3 prediction windows means we can span a larger length of instructions within kind of compared to our previous generation.
All right. The next two are again on AVX 512. So since the AVX 512 has full 512-bit width, how does it behave while in load? I assume there might be a higher power consumption while doing AVX 512 workloads, or does it run at a lower clock speed?
Well, I think all our cores have to manage the power of the current system, and we modulate the frequency. Yeah, with the AVX 512 full data path, that is a way to get to the maximum power that you can run. However, as you can see, we have significantly grown the integer side of the machine as well. And so actually, the delta of what you can extract out of pure integer workloads and that AVX 512 is not that far apart. And so we will dynamically react as we have to, even if you're running a high power integer workload. But it's not, we don't consider it, we'll see effects like you may have seen on previous generations on competitors who I would say added it too early when it was way out of balance compared to the general delivery of performance of the rest of the machine.
All right. And then can you confirm that Zen 5C has a 512-bit data path for AVX 512 as well?
So the Zen 5C used in Strix has a 256-bit data path, and so does the Zen 5 used inside of Strix. So there's no delta as you move back and forth in vector throughput. And you get the area advantage to scale out a little bit more.
Okay, and you may have already answered this, but I'm not smart enough to know that. So are the classic cores in Strix Point physically capable of doing AVX 512 single cycle, or are they restricted to the rate of the compact cores at BIOS level or boot up?
They are fully restricted. They cannot be configured to run at a different vector width than the Zen 5C.
Physically,
All right.
yeah.
Physically removed, right.
Mm-hmm.
Switching topics a little bit, can you confirm that there's no change to the IHS design and the TIM on Ryzen 9000? The thermal improvements are due to floor planning and sensor placement?
I would say majority of the lion's share of the improvements came from that. But yeah, there's no meaningful improvement on the infrastructure, the physical infrastructure that you just described. Yes, I can confirm that.
Okay. What are the typical and full range for Zen 5 misprediction latency? Zen 4 was 12 to 18 cycles, with the common case being 13 cycles.
Yeah, I'm not gonna reveal that today. I mean, you guys can have fun trying to figure that. I will say, I think you will see on average an extra cycle on Zen 5 due to just sort of the additional all the changes we've made. Although we know we're very sensitive to that, so that's one of the things we obviously will be working hard on to optimize as we go forward.
Okay. What is the reason for a 8K L2 B2B when your L1 B2B is 16K?
Well, I mean, you can think of it as, it's our L1, just like caches, are the lowest latency compared to the L2. And so we want to get as many entries into the L1 as we can. And then we use the L2 BTB in this hierarchy just for more coverage. And so unlike a traditional cache, it doesn't have to be bigger, right? It's things we've learned. We couldn't fit them all on the L1, so we have a victim L2 to store them in, but there's no reason why it needs to be bigger a size. We'd rather spend the area on the lower latency one if we can make the cycle time, which we could, so.
Okay, next one. Is the Strix Point scheduler set to address Zen 5 cores first or Zen 5C?
It's going to depend on the application and how the OS expresses its QoS level, QoS level, and its priority, right? So we're going to, and there is a mechanism by which we express the capability of our cores, and the scheduler, Microsoft will determine what is the priority needed for a process that it's bringing on, and depending on that, we're going to decide, where to put this, where this process gets scheduled. For the most part, we'd like in a perfect world, if we can handle it, we will have everything run on the compact core or the C cores. That's our intent, because we believe for that the power performance curve at the lower end of that power range, if you will, it is more efficient, as Mike had shown. The efficiency of that code is slightly better. So for mobile, Strix Point in particular, we would like to run compact cores as often as we can, but the determination of whether it runs there or not will, like I said, has a handful of factors, which includes what the OS believes is the QoS and the priority needed for it. And if they specify the latency needs to be short because that matters for user experience, it'll pick up on that and make sure it gets scheduled on a classic core, right? But the intent is for us to try to use the compacts as much as possible. But again, use the classics where it's needed so that you don't miss out on the responsiveness.
Okay. Is the Infinity fabric between the IOD and CCDs still 16-bit cycle write and 32-bit cycle read with the dual CCD layout?
And can never get anything past you guys. Yes, it is 32 bytes per cycle on a read and 16 bytes per cycle on a write. Again, the history for folks there is it is a die-to-die. Like I said, a fabric interconnect, which means there is a PHY, there is a SerDes there that's running at high speeds, and the number of lanes you want to use on that SerDes, we have to minimize for power consumption as well as package fit. So when we looked through all the data ports now in a monolithic chip, you can just connect the thousands of wires that you need for 32 bytes, 512-bit data path on both directions. But as you look towards a die-to-die link, we always look to optimize both for power as well as fit. And from a performance standpoint, we know that normally there's a 3:1 reads to write ratios that's there. So we did a lot of analysis around what happens to if a data path the write data path gets cut in half, and it did not impact any of the known workloads because you had, like I said, a mix of reads and writes that allowed us to make sure that the writes were not getting blocked. If you have reads. Now, if you're doing writes 100% of the time, you're probably doing something synthetic. You should really be bringing data in to operate on it and then write it back. So this has served us well in the last couple of generations when we had this die-to-die interconnect link, and that we've continued that with this generation. So yes, 32 bytes per cycle on reads and 16 bytes per cycle on writes, but again, should be seen as a power efficiency improvement without hindering performance. That's why we did it that way.
All right. This one's a little bit of a lengthy one, but let me give it a shot here. With Zen 4 and Zen 4C, the area difference between the two core types was about 35%. Looking at the Strix die shot, it looks like Zen 5 and Zen 5C are almost the same size, apart from the L3 cache, of course. Am I correct that the area difference is much smaller? And if so, why is the size difference so much smaller than with Zen 4 and Zen 4C?
So I'm not sure which die shot are you just referring to, Mahesh's toy block diagram, which was not drawn to scale. But yes, I think, as I tried to hit on, when they were in, homogeneous SOCs, we could really have more degrees of freedom, let's say, to reduce the max frequency and go after a more homogeneous throughput-oriented machine. In the heterogeneous machine, we have to be careful that, as you move, let's say you have 4 threads running on the 4 classic cores, as you move to that 5th compact core, you don't, your frequency has already been pushed down by the TDP of 4 classics running, but we need to have a nice smooth transition to that 5th one and 6th one and 7th one so that, true multi-threaded workloads that are actually treating this as a homogeneous design, splitting up the work across them, expecting them to all run the same, they get that feel and function, or one doesn't really stick out and then run at the order of the slowest one. So it is true. The picture is not to scale. I would say, it's ballpark-ish, still a good, 25% delta, and that's a ballpark number, but it's not that because, it's because of it needing to exist in that heterogeneous machine. And if we put it in a homogeneous machine, you might see that we change the compact view as well for that particular machine.
That's right. And Matt, if I were to add, I think the design requirements that we placed in front of Mike for the compact core was based on its voltage frequency or a performance response. Just want to make sure that's clear. That was what was in the bounding box. It wasn't area, right? That we got some area in return because of the optimizations that we did in terms of moving away and trading off that peak frequency for some area was a nice, I mean, it had to happen. It was physics. So we got that, but I don't think we drew a box to say we needed to get this amount of area savings. We were really focusing on delivering the experience in terms of efficiency and performance. And as Mike said, the compact core is not closer to the area of the classic core by any means. It is definitely noticeably smaller. When you get an actual die shot, you might be able to see it. But yeah, the design points for the core was based on performance and user experience rather than area. So.
Okay. I think we're going to try to squeeze 2 more in. So I know we went over this, or you gentlemen went over this on stage, but I think it's worth repeating. So why doesn't AMD develop a smaller CPU core for use alongside the standard Zen 5 CPU cores instead of just compacting the Zen 5 core down?
Well, so I mean, That would be, you're saying, a unique core design with unique IPC properties and obviously way better power efficiency. So we certainly look into designs like that. It obviously does, as a unique design, it can't really be exposed to the general applications, at least in the way a multi-threaded application would like it. So that adds some complexity. But I would say, we continue to look at different core designs and evaluate their ROI of a unique core design like that versus what we can achieve without bifurcating the microarchitecture.
All right, and I think this is going to be our
Do you want to
last
say
one.
anything, Mahesh?
Oh, go
No,
ahead.
Okay.
no, that's exactly right, Mike. And again, designing to what we believe are the right points in terms of ROI at this stage is what we are going to look at. And as Mike said, we are constantly evaluating and making the right trade-offs in terms of resources to make sure we have the right IP to succeed.
All right, and I think this is going to be our last one along similar lines. So do you use something similar to Intel's Thread Director to optimize thread scheduling between Zen 5 and Zen 5C?
I would not say something like Thread Director, but yeah, we have our own mechanisms by which we communicate to the OS our capabilities. There is a structure that we populate in memory, and our system management unit maintains that. And there is communication with the OS, and we are constantly tuning and tweaking that to make sure we get better and better in terms of behavior. And yeah, we have weights, we have ways in which we can express our cores and the tendencies with which the scheduling needs to happen, either based on history-based mechanisms or just power perf. How many cores are running versus what needs to come on, the amount of TDP left. The system management framework has all of this information, so the same decision may not have to be made every time. It depends on what else is running, what else was run before. Is there a context we need to be aware of? So it is complicated. We have our own mechanism in place to do that, and I will say that it will continue to evolve as we get updates out, as every step of the way, whenever the next OS comes out and so on and so forth. We're going to constantly keep tweaking that, and we have control on our end in terms of how to express this. But we're working with Microsoft as well to say, once we express it this way, employ so in order to schedule the process on the right core. So I think that's the way I would answer it. I would not talk about it in any sense in the same sense as a thread director, because that's not what we wanted to be compared against.
Awesome. Well, Mike, Mahesh, I really want to thank you for your time today, and thank you everybody for joining us. A copy and a recording of this deck and the presentation today will be made available to you. Just as a reminder, the embargo is going to be this Wednesday, the 24th at 9 a.m. Eastern, so that everybody has a chance to digest everything that was discussed today and do any kind of write-up you may want. If you have any follow-up questions or anything that wasn't answered during the Q&A, please follow up with your PR manager. And with that, I'll wish you all a great rest of your day. Thank you, everybody.
Thanks, guys.
Thanks. Bye.